All right, logic world. Unfortunately, this is like a lot of me talking and not writing. I'm going to try to find things to write. But logic is a completely different world than sets and things we've done so far. It is using logic. There's a hard way to describe it. It is just a way of deciding. A lot of what logic has to do is like true or false. Like we're trying to determine if things are true or false. So the first thing we got to do is like figure out where we use logic. So a statement is, I guess, any sentence. Probably sentence is the wrong word to use there, but that's fine. Any sentence that can be true or false. Okay. So if it's a question, if it's a command, if it's I don't know what you call cowabunga. You English people can tell me what you would call that. But a question or a command, like if it is objective, then it's going to be a statement, right? If there's a way that you can prove that it's true or false, there is data you can show, then it is true or false, then it would be a statement. If it is subjective, like someone's opinion, it would not be a statement, right? Okay, so cowabunga is not a statement. You cannot prove cowabunga true or false. Y'all are probably too young to even know what cowabunga is. Do your homework. Do y'all know what cowabunga is from? Okay.
Yeah.
Okay. Okay, yes. I guess Seth Rogen just had the one, right? Do your homework. That is not a true or false, right? That's a command. Is your house painted blue? That's not a statement because that is a question, right? Math facts are, this is where I shouldn't have used the word like sentence in my definition, but math facts are true or false. They're called math facts, right? So like that is a math statement, can be proven true or false if it's correct. Like that one is, even though it's false, like 40 divided by 8 is not 7, like we can say that's false, so that is a statement. A statement can be true or false.
It could technically be written as a sentence, though.
It could be written as a sentence. Vietnam has the largest population in the world. That would be a statement as well, because you can easily determine if that's true or false, right? Okay, so a statement is anything that can be proven true or false. All right, so a simple or compound statement. Have a good one. I actually want to go. I should have screenshotted this. I forgot to. A simple or compound statement is anything. A simple statement is one that has. Did I not get all that? Sorry. A simple statement is a statement that has one statement in it. Okay, it has a one-part statement in it that can be proven true or false. A compound statement is more than one. I was going to say, it says 2 or more right there. So I don't have anywhere to write that. I'll have to write it in just a second. So compound has more than one, and a simple just has one. So that's how you determine if it's a simple or compound. These are kind of the key words that they use to determine the different types. We don't go too much into this. This is more English than I like, but we may see these words every once in a while. A conjunction is and, but, or yet. Okay, a conjunction they use and, but, or yet. So the two statements they have here is Tim is running and Tim is singing, right? Tim is running could be proven true or false. Tim is singing could be proven true or false. So that makes it compound because I'm putting two together. Okay. These are basically saying that the whole sentence is either true or false, right? Because it's the word and. It's combining both of these. So for the whole statement to be true, like Tim would have to be running and he would have to be singing for the whole statement to be true. Disjunction, they use the word or. This one's a little bit different because as long as Tim is running or Tim is singing, the whole thing could be true, right? As long as one is true, the whole thing would be true. And then those are the main ones we're going to talk about today. Next week, we talk about the conditional. Conditional is based on a condition, if, then. So if Tim is running, then Tim is singing, right? Like Tim has to be running in order for Tim to be singing. And I do not remember if we do if and only if in this class, but biconditional is like, so like in the if-then statement, it's if this is happening, then this is happening. Like if the first one's true, then this one is true. A biconditional, it works both ways, okay? So it would say the second one also has to be true for the first one to be true. So Tim's only running if and only if he is singing. So let me save this in here before we go to the problem. And let's write this real quick because we didn't write this. Simple is one statement, and compound is more than one statement. I think that actually the way they say it is two or more. I don't know, more than one should work too. All right, so let's go to the question actually. Back to the question. All right, playing golf on a rainy day is not my favorite thing to do. So the only thing that can be proven true there, this is kind of tricky on this one, but the only thing that can be proven true there, I went ahead and solved this. We have the answers and talk about it. Playing golf on a rainy day is the only thing you can do. Like, you could say, are you playing golf on a rainy day? That's true or false. But the favorite thing to do is an opinion, so there is only one thing that can be proven true or false there. And really that is completely, well, it's not wholly, or I don't know. But there's only one thing that can be true or false there. If they get on, B. They will get train passes or we will rent a car. So you have two completely different statements there, right? The train pass can be proven true or false. The rent a car can be true or false. So that is compound. And that word or right there is going to make it disjunction, okay? So once you choose it as compound, you will have to choose whether you are, what type of compound statement it is. So that will tell you your answer. So here the word or makes it disjunction. You should sign the contract if and only if you agree to the term. You agree to all the terms, okay? So you can sign the contract, or you could agree to all the terms. Like both of those could be true or false. So, but the if and only if tells us that it is biconditional. So again, what you're looking for here is a compound one has two different things that could prove that could be true. So this is like one, and this is two. Okay. All right, the next one is a negation of a statement. So the negation stuff is probably the hardest stuff that we do today. The negation stuff is, I feel like my cord is fixing to go. I might have to buy a new one. For a negation to happen, how do I say this quickly? Their truth values are always opposite. Okay. For a thing to be, or for a statement to be a negation of the other one, the truth values are always opposite. So if I can say that one's true in this case, the negation would be false. Or if it was false, then the negation would be true. And there is no scenario where they could be the same. One scenario where they are the same. How do I say that? I'm trying to say it fast. One scenario where they are the same proves, I guess, it is not a negation. Okay. If you can find one scenario where they'd actually end up being the same, then it is not a negation. There's probably one that'll trick me up here because they're just hard to think about. But our original statement, it is not the case that I am drawing a rectangle. Okay. Bless you. So if we thought about this in just like came up with our own, it is not the case that I am drawing a rectangle. The opposite of that would be I am drawing a rectangle, right? So that's kind of what we're looking for here. So this one, the first statement, I am not drawing a circle. Well, just because you're not drawing a circle doesn't mean you're not drawing a rectangle, right? Like you could be drawing a triangle. I am drawing a rectangle. That would be a negation. So that would work. So that's every time this is true, that's the only two scenarios that can happen, right? If I am not drawing a rectangle and he is drawing a rectangle, then we are negations of each other. Like that is, like there's no scenario around that. It is not the case that I am drawing a triangle. Okay. Well, just because I'm not drawing a triangle, that might mean I'm drawing a rectangle. It might not mean I'm drawing a rectangle. So there is a lot of different scenarios there that would prove that they are not negation. Here's the one that messes with you a little bit. It is not the case that I am drawing a rectangle. Okay? So I'm not drawing a rectangle. If he says that I am drawing a triangle, oh man, this one's easy. Then it's true for both of us, right? Like we'd have the same truth value. I'm not drawing a rectangle, and he is not drawing, or he is drawing a triangle, so it could be true for both of us. So that is none. That is not that like we got the easy one there. I feel like hopefully that made sense to you, but I got to get to this one where it's tricky. I don't like that it is not the case. This one right here. So I'll just talk about this. I don't have to do this one. The sign is on the table. Okay. Here's the one that messes with my brain. The first one. The sign is on the bookshelf. To me, these should be negations because I know if the sign is on the table, then if that's true, then this one's false, right? The sign is on the bookshelf would be false, right? And if this is false, if the sign's not on the table, then this could be true, right? I think I used the key word right there is could be, okay? So just because this is false and this is true and this is true and this is false doesn't mean, is there a scenario where both of these are false? There's not a scenario where they're both true, right? Because they can't, the sign can't be on the table and the bookshelf at the same time. But is there a scenario where both of these are false?
Yeah.
Yeah, what if the sign is on, I don't know, the bed, whatever. Like, if the sign is on the bed, then they are both false. So that means this is not a negation of this one, because there is a scenario there that proves that they could have the same truth value. Okay. So this is no. Because if the sign is on the bed, they are both false. Okay. So they must have, in every scenario, they have to have opposite truth values. If you could ever think of one scenario where they don't, then they are not negations of each other. All right. This last one, this is understanding quantifiers. Quantifiers are words like some, none, every, at least one, things like that. So this one isn't that typically that bad. You're just choosing which one. So some socks in the row have stripes. The word I will say, or the thing that I will denote, is in math, some means at least one. Okay, as long as you have one, it could be considered some. Okay, that does kind of help with the logic part of this. But if you have just one, technically that's some. Every sock in the row has stripes. That would be also true in the first. I'm just kind of working with the rows or straight across. Not every sock in the row has stripes. So this would be like as long as one doesn't. So not every would be as long as one doesn't, then not everyone does. So now to the next row. Some socks in the row have stripes. Yeah, there's at least one that has stripes. Every sock has stripes. No, not all of them. Not every sock in the row has stripes. Okay, there is at least one that does not have stripes. And then the last one, some socks in the row have stripes. No, because it's none. Obviously, it's not every sock in the row has stripes. As long as there's one that doesn't have stripes, it would not have stripes, okay? So they will use a lot of words like this, but the big key there is that like the some means as long as you have one, it counts as some. All right, the hard one here, and if you all want to take a picture of this or write a couple of these down, technically they're the same thing. Like the first two rows are the same as the last two rows. They just switch it, if that makes sense. Like, and which one? But now we're going to put together like the quantifiers with the negation. So these are the keywords you look for. And what you're going to look for, the opposite of sum. So that's why I stress sum is at least one, right? So the opposite of sum, or the negation of sum, would be none of them. Okay? So like the 4 sock scenarios. If I say the word sum, I could have 1, 2, 3, or 4 with stripes. That would all be sum. Okay, sum would be good there. So the only scenario that's not good there is if none of them have stripes. So the opposite of at least one is none. And that's like a weird math concept that you can talk about there. But at least one would be 1 all the way to the end. So the only thing that's left is down here is a 0. So on the reverse of that, this is, I feel like there's an easy way to write this out. And I maybe should have done this last class. But if I have the numbers, these numbers right here, okay? Sum, all of those count for sum, right? So the only thing that doesn't count for sum would be this right here, would be none. That would be the negation. And maybe this is because my brain does math, like I think numbers, but this is the way that I think about it. So in the other scenario, if I had all, the opposite of all would be some, do not, or like not every. What other words do they use there? Not all. Okay. So like that's kind of the different scenarios there. Is like the opposite of some, at least one is none. The opposite of all is that at least one doesn't. Those would be negations of each other. All right, let's go to the actual problem so we can see what it's like. I'm definitely solving this one as I talk about it because I'm likely to get one that hurts my brain. Okay, every contestant on the show can win. So this is where you can go to your chart and see that every and what words are the negation of every, and it makes it a lot easier, okay? So in my head, I think about, okay, every is like all, right? So not every contestant on the show can win. That would be the negation, right? Every and not every. That one should be easy. Those are like the same words. At least one contestant on the show could win. That is not a negation because if I go back to, I don't think I'll write anything, so let's save this real quick. If I go back to like right here, the only scenario where my negation, this is all, we're doing every, so that works here. The only scenario where I have the negation would be one of these. So like see, some actually overlaps with all. Okay, you cannot have the same there, if that makes sense. No contestant on the show can win. All right, so I had to think about this for a second. So we have this one, and it says no contestant, right? A negation always has to have opposite truth values. So if I have every contestant will win and no contestant will win, it sounds like negations. But what happens if like 3 contestant wins? Then they are both false, and they can never have the same truth value, okay? That's the way you have to think about those. All right. Some contestants on the show cannot win. You know what? When I wrote this right here, just like as I did that right here, we technically should not circle the 1 or the 0 because none is not a negation of all. Okay. Sorry, back to this. Some contestants on the show cannot win. That would be a negation because either every contestant wins or some of them win, and that's some cannot win, okay? So you would never get every, and they can never be the same. Some could not win, maybe 0. Yeah, maybe we should keep that highlighted there. See, now I've got myself all messed up there. Technically 0 is possible. You just got to be careful with it. Because that's going the other way. Yeah, so some contestants on the show cannot win, right? You could have one that doesn't win, or you could have two that doesn't win. You could have zero, or nah, that hurts my brain right there. Okay, so this is where, like, those words, if you do struggle with it, some contestants on the show cannot win. I know it's opposite because it's always going to get a different truth value than all the ones win, right? We could go through all the different scenarios. Does that make any sense at all? I've noticed with the truth value, not on that one. Do we need to think about this more? Anybody? Any of y'all awake over there? Every contestant on the show can win would be all the winning. Some contestants on the show cannot win. Some contestants on the show cannot win covers all the other scenarios except the all. Does that make sense? So that is why it's a negation. There is no scenario that can make both of those be true. Some contestants on the show cannot win would cover all the other scenarios. That's why it's a negation. And it's the opposite. It's the opposite of all, and it can cover all the other scenarios. This topic is probably the hardest topic that you do all day, just to let you know. Told you I'd get stuck on one. All right. In sets, we had the union and the intersection, right? The union and the intersection, the union was or. In logic, we use that V symbol right there in the blue. This V symbol right here, and it means the same thing. It would mean or. So if it's like an upside down V, it means or. In sets, you have the upside down U and it meant and. So here it's the upside down like V symbol, like the up caret symbol. It is and. Okay. So just different symbols. They always use P and Q for our symbols here. So like P and, I'll just write P, comma, Q are statements, okay? They always use P, Q, and R. I don't really know why, but they just do. P, Q, and R are like statements. So those are statements. So you have P and Q, or P or Q. And then the last one here, with the apostrophe, we did not R in stats, or in sets world. They do a squiggly line P, and that means not P, okay? So kind of the same words, but just a little bit different symbols. So what you are doing on this first one is coming up with the different symbols. This is just a basic one. It's pretty easy. So P is there are penguins at the zoo. And Q is there are bears at the zoo. So let's make P be red and Q be blue. So we see this. All right. So there are penguins at the zoo. Okay, penguins at the zoo, and there are bears at the zoo. So there's my P and Q. So we have P and Q, but then you have the or, and for the or, we use this symbol right here. These should be pretty basic on these. There are penguins at the zoo, and there are bears at the zoo, and we have and, so it's the upside down one. So P and Q. This right here says not Q. So this would be, not Q would be something like, there are not bears at the zoo. Okay, so it's going to put a not in there. It could also say things like, it is false that there are bears at the zoo. So anything that puts a not in that sentence. All right, same thing, but a little bit harder. I don't want to get too color-coded here, but I think that was kind of nice to highlight those. So we'll do the same thing. Red is P, the path is on the park. Blue is Q, a tree branch is above us. So it says, it is false that, quotations, that quotations is a key to use parentheses, okay? So when you see quotations, I would think about using parentheses. All right, a tree branch is above us. A tree branch is above us is Q. Okay. And, sorry, I'm going to write this a little bit over here so we can, so there's my and. So it's and then it is the path is in the park, which is P. Okay. But we also have to do, it is false that. Okay. So it would be not Q and P. So the not would be outside the parentheses and the Q and the P would be inside the parentheses. Okay. Just to like write that just so it's not so spread out, but not Q and P. All right, next one. The path is not in the park. Okay. The path is not in the park. Tree branch is not above us. So the thing here is we have these nots. And then we have an or. Oops. So or is a symbol right here, or the upside down, or not upside down, the right side up V. The path is in the not in the park would be not P. So not P, I'm getting carried away with my colors here. The tree branch is not above us, so that's Q, but you put a symbol with the not. Okay. So not P or not Q. So every word in there does like account for either the statement or not, or the conjunction or disjunction. And the last one here, Q is the tree branch is above us. So a tree branch is above us. Tree branch is above us. You have or, right? That's or. And then the path is not in the park. The path is not in the park. Okay. So you just account, like I said, that symbol accounts for every word in there. All right, I think it's time to move on to truth tables. Truth tables is going to be the hardest part of this test, probably, besides that understanding or negation quantifiers. But a truth table. So here's how every truth table is set up. A truth table is all the scenarios for two different, I highly recommend writing down these rules, by the way, as I talk. All the scenarios for two different statements. So you have two different statements here, P and Q, okay? So if I were to put P and Q together in a compound statement, here's all the different scenarios. They could both be true. P could be true and Q could be false. Or P could be false and Q could be true. Or they both could be false, okay? So what a truth table does is it goes through every single scenario when you combine the statements, okay? Alex has a really cool tool to help us do this step by step. But what you always want to do is break it down to these three main steps. We will add one, maybe two steps to this next week. One for sure, but these three are the ones that we're doing this week. Okay, P and Q. For the statement and, I need this and this to be true for the whole thing to be true. So it is only true when they're both true. Okay, P and Q, so when you see the and, it is only true when they're both true. So the only scenario that these would be true would be in this one right here. If they're both true and it's true, okay? Now the way that I remember the P or Q, this is not something Alex will show you. This is why I told you to write these rules down. Since I remember and is they're only true if they're both true, I'm going to remember or is the exact opposite of that. The word for or we can think about this real quick. But for or says, as long as this or this is true, then the whole thing is true. So if they're both true, it would be true. If this one is true, it would be true. If this one is true, it would be true. So the only scenario where it's false is if they're both false. So that is the way that I remember it, and it makes sense in my head. Y'all do whatever it takes for you. But for and, it's only true if they're both true. For or, it's only false if they're both false. Okay? And then the not P, that's super easy. You just do the opposite. So if I was doing not Q, it would be false, true, false, true. But you, like I said, you got to do whatever you can to help to remember those different symbols, and then it makes truth tables pretty easy. Introduction. Okay. So Alex starts off super easy, just going through those rules basically. But what you have to do here is I need to look at, well, let me highlight, no, like I need to, so for this not P, I'm only looking at the not P, that third column there, which means I need to pay attention to the first column. So I'm going to look at the first column and do the exact opposite. False, false, true, true, okay? So what you have to do here is when you get these all mixed together is only pay attention to what you need to. So in this P and Q, I'm going to look at the first and the second column, right? I don't care about that not P anymore because that has nothing to do with what I'm looking for. So P and Q, my rule for and is it's only true when they're both true. So this would be true, and then all the others would be false. Okay? They are independent of each other. Like the third column does not affect the fourth column on this. Okay, so I fill out the third column, and then I look at the fourth column, and I say, okay, I need to use the first and the second column for this. I'm not even looking at the third column. That is one thing that is confusing about truth tables is you just have to identify the ones that you're looking for.
Why is the first one true?
What'd you say?
For P and Q, why is the first column true?
The first one is true because when P and Q are both true, it's true. That's the only time it's true on there. So let me highlight it here. You can see it. So I'm not paying attention to this at all. Like I'm not even looking at this, okay? I am looking at P and Q. So I'm looking at P and Q. So when it's only true when they're both true, okay? So that's the only scenario. That's like my rule. It's only true when they're both true. So when these two are both true, I get true for my answer.
And when they're both false, they're false.
The way that I remember it, is this. It's only true when it's both true, so all the others are false.
All right.
If that makes sense. If you want to remember it a different way, that's fine. But I'll start confusing myself if I try to do different ways. Let me look real quick. Are you kidding me? I just want an or. There we go. So on this one with the or, so the rule for or, this is the V. It looks like V. The rule for or, it does not matter. The order does not matter. So it does not matter that it's Q or P, okay? This week, the order doesn't matter. When we do if, then the order actually matters because if this happens, then this has to happen. So this has to happen first. But the order does not matter on the and the or, okay? So our rule for or is it's only false if they're both false. So that's the only scenario where it's false. All the others are true. Because all I need is one or the other to be true, and the whole thing would be true. Make any sense at all?
Yeah.
Okay. So Alex will always give you those P, Q columns like that. Like you do not have to come up with every scenario. But that is, I do like the thought process of that is every scenario possible for the two statements. Like they both could be true, they both could be false, they both could be false. Or one could be false, the other could be true, and vice versa. All right, so let's move to a little bit harder one. I'll show you what Alex does here. Oh yeah, well, we got a hard one to start. That's fine. So when you get to a harder one, this one, if you were saying this, it's like that quotation one. It is false that it is not P or Q, okay? So there's a lot of nots and P's and Q's and ands and ors and all. Okay, what you have to do is do it step by step. You have to add some columns in here. On this one, I'm going to actually add 3. I don't know, y'all are the lucky ones. I don't think last class had 3. But I'm going to start like order of operations and do inside the parentheses. The first thing I'm going to find is not P. And you can add these not graded columns in here. I know y'all don't like to write a ton of stuff down, which is fine. I don't either. So I'm going to use this right here. I'm going to do not P first. So I am looking at the first column. I'm looking at the first column and doing the opposite of it. Right? Y'all with me so far? Okay, so I'm only looking at the first column and doing the opposite. False, false, true, true. All right. So here's where things get a little tricky. Now I'm going to do the inside the parentheses. Not P or Q. So now, which columns am I looking at to find my answer here? First, second, or third? I actually need 2 columns.
The first.
Not the first. No, I kind of gave away the answer there. I need to look at the third column and the second column because I need not P or Q. Okay? So I need this column and this column. I do not even pay attention to the first. Not P or Q. I'm only looking at the second and third column right here. Does that make sense? That is where you have to start doing this with these truth tables, and that's what gets hard, is you just have to identify the 2 rows that you're looking at, because it'll always only be 2, because we're doing 2 statements. You identify the 2 columns, I said rows, 2 columns that you're looking at, and only look at those 2 to get your answer. So I am looking at the third column and the second column. So what's my rule for or? It's only false if they're both false, right? So true and false would be true. Here's false and false. That'd be false. True and true would be true. False and true would be true. It is only false when they're both false. Oh, and actually I don't need this column, do I? So now I have inside the parentheses, but I need to do the opposite of that. So all I'm going to do is the opposite of my last column there. Okay, because I want the not of not P or Q. So I just do the opposite of that fourth column. Y'all with me? Maybe. The good news is, well, not the good news, I guess, but we do also do truth tables next module as well. So you will see all this again. So again, just to like look at this, not P or Q means I'm looking at this column and this column. All right. I'm doing the not, you can't hardly see that, can you? I'm doing the not of this right here, the not of this up here, so I just need to do the not of this column right here. So just the exact opposite on these. Okay, that is why I do it step by step, to make it easy. Do small steps. How do you say that? There's probably like a profound way to do that, or say that. Probably some famous saying that I just don't know about, but it's easier to take small mini steps than it is to take one big step. Like there, life goals right there, life thoughts. Do one more of these real quick. So on this one, you have the nots in there. So the first thing I want to do is find not Q, and then I'm going to find not P, and then I'll put them together. So not Q is the opposite of the Q column. So on this, like for the knots, I'm only looking at like one column. Okay. The not P column is the opposite of the first column. And now it makes it very easy to find this last column because I'm saying, okay, not Q or not P. The rule for or is it's only false if they're both false. Okay, so I'm looking at the third and fourth column, the not Q and P. So they're both false there. True, false would be true. False, true would be true. True, true would be true. It is only false when they're both false. All right, a couple more topics, but they go quick, I think. Let's go to this one first. All right, so I do not make you do 3 statements in this class because there are 16 different rows and they're super long problems. Because you got to go through all the scenarios. All 3 could be true, or P could be true and Q and R could be false, or P and Q could be true and R could be false, or all could be false, or these 2 could be true. So there's like 16 different scenarios. So, but they do. Alex has these problems where you have to do just like one row of it to see what it would look like. Okay. So in this one, not super hard. You just have to identify the correct column to look at. Okay. So R or P. R or P would be, let's see if I can do this. R, why is that so small? R or P, okay? What's the rule for or? It's only false if they're both false. Okay? Now I have R or P right here. So now I'm going to go look at R or Q and R or P. So I'm looking at true and false. So for and, so true and false would give me false, right? It's only true if they're both true. All right, next one, not A should be fairly easy. That's true. Not A and C. So not A. Oh, wait, not A. Not A is this one. Not A and C. That'd be true, right? Because when they're both true, it's only true when they're both true. Okay, but this one says the not of that. Well, that is just the not of this column right here. That's just the not of this column, so it would be false. And then our last one, I know it looks like a lot, right? B or not A and C, like that's a lot, right? But we already have done all of this. So all I'm really doing is looking at this one and then B and saying, okay, F or F, the rule is for false is only false when they're both false. So you just have to identify which column to look at there and take it piece by piece. This one already sets up the steps for you, so that makes it nice. All right, De Morgan's law. De Morgan, some dude that always pops up in logic. If you want to take a picture or write this down or whatever. But his laws for logic is just kind of a shortcut. This is basically saying you have two logical statements are equivalent when you have the same truth values. So if we did a truth table for this side, it would be the same as this. Like if this one ended up being, I can probably do it real quick. This one would end up being false, 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 true. Okay? So then if I did the same thing for this one, it would be false, 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 true. And that makes them equivalent. So this always works out. Now here's how my brain does this. This doesn't really work mathematically. It does not work like this, but this is the way my brain thinks. Is if I distributed this negative or this squiggly line through and then flip the sign, that's kind of what happens. It ends up being the same. And the same thing down here. If I were to distribute this squiggly line through and then flip my sign, it ends up being the same thing. Okay, so that's just the way like my brain sees it. Whatever helps you remember that. But basically it's saying is, if I say it is false that P or Q is the same thing as saying not P and not Q. Okay. So whatever helps you kind of remember that, you can kind of think through it too. It's just a shortcut. I'm going to go ahead and click solve here. Because I know this one messes with my brain. Part A, and I didn't realize this last class, but Part A says that use De Morgan's law to choose a statement equivalent. So if I say novels aren't true stories or there aren't 4 books in a trilogy, this would be something like not P or not Q, okay? Not P or not Q. So if I want to go back, what I would do is say P, flip the sign Q, and put the not in front. Those two would mean the same exact thing. All right? What I missed on this one last class until I realized it is this says the negation. The negation is going to be very similar to the same thought process, but let's write it out real quick. So they own a car and we have a garage. Okay. So it always has to do with flipping the sign. So it's going to be P or Q. Actually, sorry. This one has no squigglies in it, but if I flip the sign and put nots in there, it ends up being the negation. That's the way that'll always work. If you put the negations in there and flip the sign, it will end up being the negation. Okay. So they don't own a car or we don't have a garage, is the negation of they own a car and we have a garage. It's always the same idea. Flip the sign in the middle and put the squiggly lines in there. And the very last one is kind of the idea of why we have to do this in real life, or why you're doing this in class and how it works in real life. But it is actually giving you some data to work with here and saying, okay, let's set up a statement and see if it works. No, you're not going to write out P and triangle Q in real life, but you're going to think about these things, right? The bar graph shows how company divides its annual budget by departments: support, engineering, research, sales. Okay, P is the company budget. P, the company budget's the least amount of money for is engineering. The company budget's less amount of money for sales than research. So now let's write this sentence right here. The company budget's the least amount of money for engineering was P, and the company budget's less money, and the company budget's less money for sales than research. So that would be Q. Okay. So now I'm going to go back and say, okay, is this statement true? It's an and, right? Oh, wait, I did or. I did the or symbol. It says P and, right? Is this true? Okay. So we know from and that both of those statements have to be true for the whole thing to be true. So let's go back and think. Is P true? The company budgets the least amount of money for engineering. Is that true? That is false, right? Engineering is the highest bar. The company budgets, so what about Q? The company budgets less money for sales than research. That would be true. The research bar is bigger. So now I think of my rules, P and Q. It is only true when they're both true. So this whole statement is false. Okay? And that is my answer there. So you actually have some data to go determine if the statements are true or false, and then you get to think about whether these are true or false. Now what was funny, or the way, this is kind of terrible to say, but last class we got an or, right? So or says that only one or the other statement has to be true for the whole thing to be true. So basically you could kind of make up whichever you wanted for the first statement, and as long as the second statement was true, technically if I say, I don't know, I was trying to think of an example. The sky is purple and the grass is green. I'm sorry, the sky is purple or the grass is green. Like that whole statement is true because the grass is green, right? It doesn't matter that the sky is not purple. So that is kind of like a weird thing. When you use the word or, only one or the other one has to be true for the whole thing to be true.